I like it. Indeterminate form, but more specifically.
Fraction.
Yeah, indeterminate form that's in the form of a ratio, right? Because L'Hopital's is all about ratios of functions, and they're competing as to who can get to where they're going faster, right? So we've done problems like this. What you got, Jeff? I can't. There's really nothing else that great about. Let me think. Screw it. I mean, there's one on the test just like this. And is this in an indeterminate form, first off? I had a few too many people tell me, well, this is 0 times something, so the answer is 0. Why is that not good enough? Because what is this something doing? Be a lot more specific. Negative infinity, right? So 0 times anything is 0, sure, but negative infinity isn't anything. It's a process. It gets huge, so you don't know. All right. So how do we change this so that I can use L'Hopital's? L'Hopital's needs to be a ratio.
So for 1 over L of x. How do you know?
Ln of x over x to the negative 7.
Yeah, so it'll be ln x over. Now you can't just do this. All right, so I had a few too many people just say this. I love this. This is all. You're like, yeah, times is divide today, Jeff. All right, we all know that's shit. Yes?
Yes.
All right, so to keep it legal, I want to divide by something that would become x squared. So I divide by its reciprocal. What form is this in now? Negative, be more specific. Negative infinity over, which is infinity. You can say that when we're talking about the form it's in. So I cannot plug infinity into anything. I cannot plug infinity into anything. I'm writing in little parentheses what form it's in. That's fine. Okay. And now you just attack the top and the bottom with derivatives because now L'Hopital's rule applies. All right. And one extra little thing, if there's a 7 here, you could just pull that out because it's just a constant, right? The limit's just going to attack the part with an x in it. Okay, so that should help out. What number is that again? 5? Okay. All right. Any other general questions? Yes.
So is there like a mathematical way to do number 6?
I'm sorry, I was gonna. No, it was a philosophical way. No.
It's like one of the only
There's a
ones I got right.
culinary. There's a culinary way to do it. You had to identify the recipe. No. So I told you should draw a rough sketch, and some of you guys might have been like, I don't know what the hell. I'll just put it in the freaking calculator. Why not? I didn't say you couldn't use one. But more better. I love it. Better than that. What do you know about this? You don't know what it looks like, but what else did I tell you? What other constraints are there? It has to be in the first quadrant. So what's a really smart thing to find? Probably x and y intercepts, right? It's one of the first things you find when you're trying to graph something. So take your function, let x be 0, let y be 0. That gives you some stuff, and then you basically, it almost doesn't matter. So if that's the y-intercept and that's the x-intercept, it almost doesn't matter how they connect, because you're just going to draw your rectangle in, right? I can find one more point in the middle to get a little better idea of what it's doing. Are you guys at all with me? Now, how wide is this? Do we know? Why did I put it where I put it? Just because I don't know where it is. I'm just going to put it somewhere. So this is x. I like it. And how tall is it? Holy shit. And do we know what y is? Didn't I tell you what y is?
6 minus x over x.
And why does that make sense? Because the y has to be on this function, yes? Because it's got to fit in there. It's got to be on the function. So then you know area is x times y. You can replace y with what you know it is. Take derivatives, blah, blah, blah. Okay. Is that all right? Okay. Maybe. So, I mean, yeah, I really appreciate that. I did want some kind of idea that you were trying to draw a rough sketch by hand. But if you're not sure, just put it in the calculator, because at least you can then do the next steps, right? Just put it in the calculator, go, oh shit, okay, there it is, right? It's a lot better than not doing anything. Okay. Anything else? All right, put those away. So, we still got to do 4-9. 4-9's title definitely gives it all away. This is antiderivatives. Some of you guys have taken calculus a little bit before. You know what this is going to lead to. At the moment, we are calling them antiderivatives because we have to prove some stuff later, and then we can call this a different name. But right now, it's just antiderivative. So what the shit is an antiderivative? So here's what an antiderivative is. It's, if I have a function f of x, the antiderivative would be a function, we very often give it a capital F. This would be the antiderivative of f of x if f prime of x is f of x. So given a function, can you figure out a function it would have been the derivative of, right? And we've sort of done a couple of these. And the more derivative rules you know, the more you can figure out antiderivatives, because it's just going backwards. And bless you, how does this go in keeping with all of mathematics? When you learned trig functions, sine, cosine, whatever, didn't you at some point learn inverse trig? Because you have to be able to go both ways. If there's a cosine in an equation, you have to do the inverse to solve it, all that kind of shit. So we have a process derivatives. There must be an opposite process, antiderivative. So I can go both ways, right? Okay, I like it. So let's try some simple ones out. Find, I'll just put an f of x. Find an f of x for each f, little f. So when you see a capital F, that should denote antiderivative of little f, right? So what if I have this? We'll start off really nice. Yeah, where would this have come from? Yeah, it could have come from x squared. So that's good enough for the way that I put the question. Does somebody know another answer? X squared plus 7. I love it. Is everybody cool with that? Because how do you check? What's this guy's derivative? Freaking 2x. I love it. So what's the most general way to write every possible answer? Yes. X squared plus c, where c is called c because it's a constant. Kick ass. Right? So the better you know your derivative rules, the easier antiderivatives will be, which kind of makes sense. The better you knew your trig, the easier inverse trig was. Right? All right, so let's see. Let's get a little bit more interesting. What about, let's see. Oh, yeah, sure. What about this? Oh, this shouldn't be too bad. Yeah. All right, now this is where things are going to get kind of interesting. So does everybody agree that this seems to be a good candidate? Right, and how do you check it? Take derivative. Derivative ln of x is 1 over x. I love it. Now, I did make a point of this earlier this semester. Does anyone remember? I can't remember exactly the context. There's something a little weird. Can somebody tell me what the domain of this is?
Everything but 0.
Everything but 0. Wouldn't it make sense then that its antiderivative should handle the same inputs for the most part? Yes? It would be weird if I could figure out what the slope of big ass f was somewhere, but big ass f didn't exist there. Does that make sense? Are you guys kind of with me? What's the slope? All right, let me ask you this. Which one of these is the slope function?
Sorry, 1
More
over
than
x.
f of x.
That's a beautiful way to say it. F of x is the slope function. My ass is covered. I'm not going to get any more specific than that. Yeah, so little f is the slope, yes? Of big ass f. What's the slope of big ass f at -2?
-1/2.
-1/2. Currently, can you put in -2 into big ass f?
No.
that doesn't make sense, yes? Do you guys understand there's a slight issue here with a disconnect? I can find the slope of a function somewhere, but the function doesn't exist there? What the shit? How do I take care of this? We've got a problem, we've got to take care of it. How do I take care of this problem?
Absolute value.
Yes. Bam. And of course, it's the same idea. Again, what's another possible answer? The plus 7, blah, 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 and then eventually you get to, just to cover everything, plus C.
Do the absolute value because of the domain, yeah.
Yeah, you want the domain to equate, right? Between the functions, yes. And again, it's exactly what I said. How in the world can I have a slope that I can find for a function that doesn't exist at that point? That doesn't make sense, right? Yeah, I like it. Maybe. This is one of the easiest things to forget. It doesn't come up often enough to make it routine. So when it comes up and you forget, it's understandable, but that's how that really works. Okay. All right. So what about, let's make this a little bit, just a little tiny bit funkier. What about this here? I like it. Yeah, it's bodacious. Does that help or does that help? I don't know what helps. Okay. So why is this harder than this one? More stuff. I love it. Right? In fact, let me do one that's sort of an intermediate step. What if I had this? What would its antiderivative be? Yeah. All right. You know that when you take the derivative of a polynomial kind of thing, the degree goes down by 1, right? So you know this had to come from x squared. But how do you know this is not right? Because if this was right, there should be a 2 there. So what would kill the 2 that comes down? 1/2. And isn't that what we did here? We put the 2 up and we took half of 2 and got 1. I know that's not what we did. We just put the 2 back up. Right? But that really actually is the thing behind what we did. All right. And of course, then I can put my plus C. This, by the way, will annoy you. I'm going to annoy the shit out of you. You're going to lose points for not putting plus C. Yes? Because otherwise your answer is too specific. I'll say, how do you know it's 0? All right. So what about, look at this now. Look at this. Don't let that 7, don't worry about the 7, right? What must x to the 4th have come from? X to the 5th. What would have had to be out front to kill the 5 that would come down? Because there's no 5 here, is there? There would have been an over 5. I'm going to catch up to you, right? 5's going to come down. Now that we have an over 5, that's going to kill it. And of course, I want a 7 there. Bam. Okay. All right, what about this guy? Let's think about him the same way. It would have come from x to the what? 4/3. I love it. And the shortcut is when you're doing antiderivatives, now you add these. 1 plus 3 is 4 over 3. So now you think backwards. When you take a derivative, what would have come down? 4/3. And there's no 4/3 there, so there must have been a what there? 3/4. Are you guys? Isn't that kind of nice? And again, the more you know derivatives, the more you can think backwards to get antiderivatives. Okay. And of course, I better put what here just to satisfy that jackass Jeff? Yes, plus C.
Can you make your F capital?
Say again?
Can you make your F capital?
Oh, yeah, thank you. I think I tried to, and you got a little curvy. All right. So let's do this. What about, Let's make a rule. Let's make our first general antiderivative rule. If I have this, what will this be? So to go backwards, what happens to the power? It goes up by 1. But then what has to be out front then? Yeah, 1 over n plus 1. I like it. So, and of course, bam. And we normally just write this like this. That is the antiderivative rule for any polynomial-looking piece. All right. So that's probably, what was our very first thing we learned the derivative rule for? All right, wait a minute. What was the very first thing that we learned a derivative rule for? X to the n. Yes? Isn't that the most basic? You could argue constant, but we actually did that after. Well, we did x to the n, we figured out that derivative rule. I like it. Is it bad if a calculus teacher can't say derivative? Is that bad? All right. Let's see. What about this? Got to keep up with my Roman numerals here. I'm already off by 1. Oh, well, screw it. What about, let's see. Let's not make it too freaky, Jeff. Yeah, let's do that. I like that. Oh, shit. Can you rewrite this? Is there a better form to have things in when you're discussing derivatives or antiderivatives? How can I put this? What form can I put this in? All right, so now I can look at it. And again, the funny thing is I kept saying polynomial with that nth power thing, but we know that it extends beyond polynomials. It works no matter what the nth power is. It could be negative, whatever. So what do you guys think about this then? What would this happen? What would happen to this? Where would it have come from? It's to a power, so it's got to be relatively easy. The power would have been 1/2. So what must have been out front then to kill the 1/2 that would have come down? There must have been a 2. Be careful, right? A 1/2 would have come down. So now I need a 2. Basically always the reciprocal. Isn't that what this says? It's the reciprocal of what the new power is. In fact, yeah, okay, I'll do that next. So there must have been a 2 out here, and there's already a 3 out there, right? Does that look good? How could I have made that a lot harder? Well, I trust in your ability to make things hard, Jeff. What's really nice about this inside? What's its derivative? Do you see how if the inside has its own derivative, it's going to make this process harder? I didn't have to take it into account because the derivative of this is 1. It doesn't mess anything up. Okay, I like it. And of course, let me bring in some trig real quick. What about this here? What do you got, Jeff? Sure. I like that one. So now what did I do? Right on the heels of what I just discussed. What will you have to take care of? I really want this to make sense. What do you have to be careful about here? What's going to be involved? Yeah, so don't worry about that right now. Where would secant squared of something have come from? Tangent. How do you know that's not the answer? Because when you take that derivative, what do you get? You get secant squared pi x times Pi. Do you have a pi up here? So what would kill the pi? 1 over pi. Do you guys, and of course, do you guys see I really want this to make all the sense in the world. It is fundamentally a secant squared. I know that comes from tangent. Cool. Then you look at what you got, you're like, that doesn't work. I need something to kill the pi that would come out because of chain rule. 1 over pi. Maybe. Stay with me now. All right, so let me give you this. Where is it, Jeff? I don't know anymore. Let's see. Here, no, that's not it. Talk amongst yourselves. Did I bring it? That would be funny. You're all like, sweet, let's go.
What happens if you didn't?
Sweet, let's go. So everybody root for that if you want to. All right, where the hell? I know I did. Bada boom, ba. Maybe I didn't bring it. Maybe I didn't bring it. All right. Well, shit and a half. I'll bet you anything it's sitting on my printer. Let's see. So it's not in here. It's not in here. Yeah. All right. Damn, that sucks. Well, it's all right. That's all right. It's not a horrible thing, Jeff. Not a horrible thing. Nobody's going to be that concerned. Yeah, all right. Damn it. I had a little worksheet, obviously, that had some examples of this, and it also kind of went into the next section. Yeah, it must be just sitting in my printer. I love it. And the neat thing is, I can't even say that's because I'm getting old, because I would do that all the time when I was younger, too. Okay. Oh, come on. What? It's just that kind of day, man. Oh, look, I got money in there. That's nice. Well, that's a good thing. All right. So let's do this. Let's do a couple more examples. Let me try to remember what I had on there. Okay. Let me think. I had a couple of good things I wanted to talk about. Rawr! Oh, what about this here? Let's see. All right, this is more complicated, yes? But let's try to attack it like we did the last radical one. How can I rewrite this? Yeah, let me give myself some more room. Yeah, x times x squared plus 1 to the negative 1/2. So become a big ass f. Okay. So let's look at this piece. Does anyone see why you should not be concerned that that's an x and not just a number? See if you guys can get it. Well, all right, let's do this. Where would this have come from? What would have to be here to get us here? You can do it.
X squared plus 1 to the 1.
Now, what do you think about, right? Is everybody cool with that? Now, we know this is not correct. Because what's happening, what do I get when I take a derivative of this? The 1/2 would come down, times this to the negative 1/2. So we got that.
But then we have
All right,
a
2x.
Yeah.
Then you're going to have a 2x. Now, so let's see. Let's try it. I kind of said something a little weird a second. We felt like it might not be right. But let's see what's happening. Let me put a little plus c in there. So if I do take the derivative, is that cool? Let's try to be a little roundy dude. Let me do this. F prime. There we go. This will be 1/2 x squared plus 1 to the negative 1/2 times 2x. And of course, this goes to 0, right? So what do you get? You get 1/2 of 2x is x. Holy shit.
Oh.
So what I want you to start noticing is, let me do this. What if it would have been? Give me just a second here. If it would have been this, bad. If it would have been this, we are nowhere near the ability to do this. Because if I try to say, okay, it came from this, do I have here what needs to be there? No. Now, I really want, there's so much happening. What did we do earlier? Like, for example, here, when we realized, so before we put that there, of course, we take this derivative, a pi happens, how did we kill it? 1 over pi. So constants are easy. I can always take care of a problem with a constant that's not right. I can adjust it, just like that earlier problem we did that had a 7 here. We just adjusted the constant to be 7/5, so it would end up with a 7. Numbers, constants, no problem. Here, I am missing something much more fundamental. Why could we do this, but we cannot do this? Because we cannot just make an x show up. It has to be there. I want that to make sense. Yes?
Can you put a 2 there and then have the 1/2 cancel the 2?
Say again?
Can you put a 2 in front of it? And then have the 1/2 cancel the 2 and then it works?
Oh, no. All right. So if I just put a 2 there, that definitely makes a 1 show up, right? But why is this not correct? Because what's the derivative? 1/2 comes down, kills the 2, x squared plus 1 to the negative 1/2 times 2x. In which case, we really didn't want the 2, right? But do you see how we don't have this? Right? Now, okay. So some of you guys might say, all right, Jeff, we don't have that. Why can't we just then come back up here and say, all right, I know this much, right? I know this much for sure. It's got to be here. There would be a 2x that comes out, so why can't I just do this, Jeff? Do you guys see that? This is remarkably wrong, and I want to show you why. Is the derivative of 7x squared very different from the derivative of x squared? What's the only difference? A number, right? You with me? How would you do the derivative of this function? What would you have to use? Product rule or even quotient rule, right? Do you think it's ever going to come out to be just this? Shit, no. Isn't this much more complicated now? So you can all day long balance numbers. What do I mean by that? It's not supposed to be a 5 there. Okay, I'll just put a 1/5 there. No problem, right? We're creating a function whose derivative would become the thing we were given. I could just put a reciprocal number there, take care of another number, no problem. But I cannot do that with an x expression because now my derivative has gotten way too complicated to ever become just this. Numbers we can handle all day long because they don't contribute anything to derivatives because their derivative is 0. The minute I try to put a function down to handle something, it's going to contribute something to the derivative. I've got to, holy shit, now I've got to do a product rule or whatever, right? Really want this to make sense. So why can't we do this antiderivative, Because what would need to be there? There would need to be an x. That's related to the chain rule piece. Okay, maybe. All right, let me try to remember. There's another example I had on there that kind of is in the same vein. Let me see if I can make another one up. Yeah, okay. All right. Wait. This is a little bit weirder to try to make up on the spot. Hold on. Let me see. Yeah, okay. Let's do one that works. What if I had this here? Where would it have come from? Sixth power. I like it. So now there's two things to worry about, correct? All right. Well, it's three things. All right, let's do that. Okay. Two things to worry about. Yeah, there has to be a 1/6 here to kill the 6 that would come down. But then what else is going to come out? 3. So you have to have a 1/6 to kill that 6 that would come down. And you have to have a 1/3 to kill that 3 that would come out. So you'd have to have a 1/18. Let's check it. What is big ass F prime? Help me out. What's big ass F prime? 6 comes down. Are you guys all right? What's happening? 6 comes down. Times 3x plus 1 to the 5th, right? Times 3. And sure enough, what's 6/18 times 3? 1. So is F prime equal to F, little f? Big ass F prime is equal to little f. Love it. So that works. So constants that come out because of powers, because of chain rule, because of anything, we can balance those out. The minute I don't have a required x piece, we are for the moment screwed, right? So just in case you're concerned, and I'm almost certain nobody is, we will eventually, actually one of the first things you learn in Calc 2, if anybody goes there, is how to do this by hand. It's pretty cool. At least I think so. I'll tell you what, you want to know what it's called? The method? You're all like, I have no idea. What is it? It's been barely any time and I feel dead already. It's called Trig Substitution. It's the bestest thing. Oh, all right, sorry. Okay. So that kind of sucks. I can't remember any of the other points I wanted to make through my examples. There was, oh, that's right. All right, let's do one more thing. What about this here? I've just given up on numbering these, by the way. What if I had this? Let's see. Let's do, sure. Let's do this. But I want to find big ass F so that I get this. Because when we do antiderivatives, do we get a specific answer? We get what's affectionately known as a family of answers. Isn't every possible answer related? Plus 7 plus 2 minus 14 plus pi plus the square root of natural log of 7, whatever the shit. It's all plus a constant. They're all related. So math people went, let's call it a family. Oh, sounds nice, right? So this is a family of functions. There's an infinite number of answers, but they're all basically the same, just one little thing. So this one I want specifically the member of the family where this is true. And there's only one member of the family where this is true. So let's just do the first step. The first step should be relatively easy, yes? Oh, this is where you're going to love this shit, right? So anytime you learn inverse anything, you got to shift gears. You are going to do derivative when you're supposed to do antiderivative. You just are, right? So what is the antiderivative of cosine?
Negative sign.
No, that is the derivative of cosine. What would I take the derivative of to get cosine? Sine. You guys understand what I'm trying to say?
Oh.
This is anti-differentiation, if you want the real full-blown word, right? This is one of the most in-your-face examples of how it can be kind of evil. You've got to think backwards. Okay, I like it. I like it. And the nice thing is this is relatively easy because is there anything to kind of take care of? No, that's it. Plus C. And now, what does this do for me? What's f of pi over 6? Sine of pi over 6 plus C. And what is this supposed to be? 1. So 1 equals, yeah, I heard it. 1/2 plus C. So C is 1/2. So what is big ass f of x? Yeah, sine of pi over 6 plus 1/2. Bam. So that is the one member of the family who made what's called, you hear this is very often called an initial condition. If you say it fast, you sound drunk. It's an initial condition. Or it's probably just me, to be honest. If I say a lot of things, I sound drunk. Trust me, I'm not drunk. Well, as far as you know. Okay, maybe. Yes?
With the sine, pi over 6 plus 1/2.
Oh, I'm sorry. I'm being really silly there. Thank you. Should be sine x. That was way too specific up there. Okay. So if I take this guy's derivative, it does become cosine, and big ass F meets this requirement. I like it. Okay, so trying to remember if there's anything else. I don't think there was anything else. No, okay. So I just want to talk a little bit about section 5.1. So again, section 4.9, it's going to be a lot easier the better you are with your derivative rules. And, oh, let me show this to you. I have a really cool little thing here. This is page 352. And they give you this rule, right? Bam, bam. One thing I want to say, so there is one condition where this rule doesn't work. So if I have this, in general it is this. I'm not surprised I forgot that because I'm a little flustered today, but oh well. What happens if n is -1 if I try to use this rule? If n is -1. What do I get? So if it's to the -1 power and I try to use this rule, what happens? I get x to the 0, right? Yes? Over 0. Plus c. And so that's shit. But we know that if it's -1, isn't that 1 over x? What is that guy's antiderivative? ln of x. I like it. So there's no bridge between positive powers and negative powers. What's the derivative of x squared? 2x to the first. What's the derivative of 2x? 2. What's the derivative of 2? 0. And then it's 0 forever, right? I can't get from positive to negative. And this is showing you can't get from negative to positive powers using this going backwards. It kind of makes sense. I can't go one way, I can't go the other. But natural log is sort of like that bridge between x to the -1 and then something, right? All right, I don't know if you guys are with me at all. But the one place that this general rule doesn't work is here, and it's very easy to see why. But there is something that does work. Okay. So the rest of this, this one, of course, kicks so much ass. right? E to the x is its own derivative. E to the x is its own antiderivative. Makes sense. The blah, 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 blah. You're not going to have to worry about trig. I didn't make you memorize these, right? And, of course, hyperbolic, don't worry too much about. Okay. So you got a nice little table there to kind of reference back to. And while I'm thinking about it, let's do that. Sorry?
What page is that?
352. While I am thinking about it, if I had this, what do you got, Jeff? Sorry. Holy crap. All right. I kind of want to let us out even earlier, and I'm sure you wouldn't mind because I'm worried about what is going to happen to me next. Okay. Can somebody figure out what that would be? I got to make these better. I'm sorry. Little f, big ass F. Yeah, I like it. So the first step is easy as shit. It's got to be itself fundamentally. It's got to be itself fundamentally. But then what do you have to take care of? Well, you got that. Okay. What do you have to take care of? The chain rule piece, right? If you take this guy's derivative, what extra shit do you get? You get a 2. So I'm going to kill it by putting a 1/2 here. So does anyone feel like you're cheating when you do that? We are constructing a function. So we can put numbers wherever. This is the point. Any number I need to balance things out, I can just throw it in there because we're creating a function whose derivative would be what I was given. If I'm missing an x piece, I am, at the moment, screwed. I have no way to do anything if I'm missing that x piece. Okay. So, real quick. What if I had this? Look at that. I love that. I really want to see if you guys get this. Now, don't worry about this for a second. Where would this have come from? It would have come from itself. What's its derivative? What would happen? Let me put this down. 2x. I have an x there, right? I have an x there. So what else has to be here? The derivative would be 2x. Do I have a 2x here? No. So what has to be here? 1/2. So why was I able to do this derivative? Because the chain rule x piece is there. So for the exact same reason, I would never, not never, we currently could not do this antiderivative. We cannot do that antiderivative. There's no way. Because if I think it's this, no, Jeff, I need 2x. I need something that isn't there. I'm screwed. I need an x piece that isn't there. And I am not allowed to do this shit. Why not? Because now that function is so much more complicated, right? I'd have to do a product or a chain rule, whatever you want to do. I get all these parts to it. It doesn't match anymore. So constants do not throw things off. Variable parts do, right? Okay, really trying to lay that groundwork now. All right. So, all right. One little thing about chapter 5, and then we'll head out. I don't want to push my luck too much. What luck, Jeff? Good point. So what's interesting is we're going to put, so 4, 9, antiderivatives. Why does that make sense? Even though I can't say it. It's because it's right after derivatives. That makes sense. When we learn one way to do things in math, we learn the other way. Chapter 5, what's going to happen is we're going to start talking about something that seems completely unrelated. We're going to start talking about finding areas under any shape. Right? And then, about a third of the way through or something through chapter 5, we're going to bring back antiderivatives and we're going to prove a connection. And the minute we prove a connection between antiderivatives and areas, we'll be able to find the area quicker. So the first part of chapter 5 is kind of like the antiderivative analogy to the limit definition of derivative, remember? You guys want to do a limit definition derivative? Do you guys, what is the limit definition of derivative? Who remembers? F of x plus h minus f of x over h, and with the what out front? Limit as h goes to 0. Okay, right? And we did some really simple functions, but have we done derivatives of much more complicated functions since then? Haven't we? Yes. We have done, you could right now tell me what the derivative of this thing is. And I can almost read somebody's mind.
Yeah.
No, listen, you could, right? That's relatively easy now, yes?
Yeah.
Do you guys agree? Because it's a product rule, you got a chain rule with the E. It's not that crazy hard. But again, I appreciate it. Would you want to do the limit definition? No. Okay. So we have to lay groundwork as to why things work. So the first part of chapter 5 is analogous to limit definition to kind of lay the groundwork of the idea. Then we get to these shortcuts the exact same way, right? So just keep that in mind in the first part of chapter 5. It's going to be kind of funky. We have to be given kind of relatively nice functions to work with because otherwise it gets really, really funky. And then we'll learn some shortcuts so we don't have to do that process. Okay. So the idea is this. If I'm given a function, right? Let me see. Yeah, let's make it. It actually doesn't need to be continuous, so I'm not even going to say that. But for the moment, let's just deal with just a nice function like that. Sure. All right. I don't know why I did that. It's too bad. It just did. All right. And I want to know what's the area under the function. I don't care about that. Let's just do from here to here. What's the area here? Now, does anyone have any trouble with why we would want to know that? Has anyone taken statistics?
I was going to say, yeah.
Oh, yeah.
Like
Yeah, well, you're basically going to learn now where all those numbers that you, for z-scores turn into probabilities, because they were all areas under the normal curve, right? The problem was, now if you haven't taken statistics, I'm sorry, but there's a whole, statistics is the most immediately obvious lower level course where you use areas under a funky looking thing. You with me? Even if you haven't taken statistics, that's a big part of it. If it's a uniform, you remember uniform? My stats people? Uniform is just a big freaking block. How do I find areas in it? I just find an area of a rectangle. Is that hard? No, right? So I'm not going to teach you stats, don't worry. Why is this area harder than this area? So why is this area harder? Yeah, this top, it's melted. Something has happened. Somebody sat on it, right? Does our geometry have an equation for a sat upon rectangle? Is that in the list? I want to see that somewhere. Sat upon rectangle. Somebody sat upon my rectangle. No. So, okay. Blah, blah, blah. So what we're going to do, in fact, real quick, let me see if you guys even know this. What's the area formula for a trapezoid? Does anyone know? Yeah, the area is 1/2 base 1 plus base 2 times the height. It's a B-headed triangle, yes? Okay. So that's why it's so close to the triangle formula. Triangle formula is 1/2 base times height. This has two bases. Do you know where that formula came from?
Yeah.
How did we derive that formula?
It's like the average of the bases, and then when you average it out, you basically get a rectangle
But why does that work? That kind of reshapes it into what?
from a curve.
Beautiful. So one way to look at this is to reshape it into a rectangle. You could basically take this piece, put it over there, or you can kind of shimmy it around. All right, something a little more direct. I'm kind of glad you said that. I've never heard somebody tell me that method. That's a good method. Is to break this up into two triangles. So one method when we have an area we're not sure about, we can kind of reorganize it. Did I show you the, all right. What's the area of a circle? Did I show you why? Did I show you guys? Remember when we cut it
Yeah.
and then we reorganized it into a rectangle? So one way to do an area we're not certain about is to take the area and smoosh it into a shape that we know. So we can take that circle area and actually cut it and put it back together to be a rectangle. Then we know the freaking area, right? Another way is to cut the area I'm given into parts. Each part I know the formula for. So let's call this area 1 and area 2. Right? I'm not going to do enough trapezoids to get to area 51. I'm sorry. So area 1, what would the area of that? I know that was a dumb joke. It's okay. What would the area of that top triangle be? What's its base? B1, right? So you have to kind of turn around and look at it like this. Its base is B1. And what's the height? Yeah. And what's the area of the second triangle? 1/2 B2 height. And then what's the area of the whole thing? You add them together and you get freaking this, right? Okay. So that's a very fundamental idea. If I have an area of a shape that I do not know, I try to cut it into shapes I do know. So looking back up here, this doesn't seem doable, right? Is there any shape I can kind of cut this into? Not well, correct? So what we do is, could I cut this into rectangles? And so here's the idea. Couldn't I cut this, let's say, let me see, I'm trying to figure out how detailed I want to get right now. Just talk about the idea. Say again?
Is that what we're doing right now?
We're doing Riemann sums? Yeah. So I have some options here as to how tall to make the rectangle. I can make the rectangle as tall as the first side. So this first rectangle would look like this. Yes? And then the next rectangle would be this tall. The next rectangle will be this tall. The next rectangle will be this tall. Are you guys kind of with me? Is this going to be exactly the right answer if I get the areas of all the rectangles and add them up?
No.
Because why?
It's gonna be a little bit of cut off.
It's a little over, a little under in some places, yes? So how could I improve my estimate? I'm going to have to fudge this a little bit. Well, not too bad, Jeff. All right. My rectangle should all be the same width, but, give me some freaking room. Yes! If I increase my resolution to infinity, dude, right? The TV, that will literally blow your brain. Infinite resolution. So how do I increase the worst resolution would be one big-ass rectangle. Why would that still do an okay job? Because my function's kind of nice. It's not that wobbly, yes? One big-ass rectangle would be kind of a bad estimate, but not terrible. So I could cut this into infinitely many. I'm not going to try to draw infinitely. So guess what's going to be involved in this process? I'm going to set up an expression for n rectangles, and then I'm going to take the limit as n goes to infinity to crank up the resolution. So, but I want you to never forget, fundamentally, all we're going to do is add up areas of rectangles. How tall is each one of these rectangles? Like, how tall is the first one? The way that I set this up. What's the height of the first rectangle? Not A, careful. F of A, right? So aren't the heights going to be F of whatever? So like, if I call the width, guess what I'm going to call the width? Delta X. Ooh. Oh, that makes sense. What's the next height? What's the next rectangle's height? Because what's the next input? Isn't the next input A plus delta X? So isn't the next height going to be F of A plus delta X? And what I'm going to do with each of these F's, am I not going to just multiply it by the width? The F is the height times the width So every rectangle is going to look something like this. So I just do each rectangle, figure out every area, and then add them up. Okay, so that's what we're going to do next time. We're going to leave a little early because I got a meeting. Plus, I just don't want to give the universe any more chances to do anything else. Okay. So next time I'll actually bring that handout. I've heard that makes it work better. If I bring them. Anybody not get their test back? Everybody got their test back? Okay.